languages in programming that you recommend starting off with for somebody new to programming? Something easy and also helpful. Is Python better,
So
or C better,
nowadays,
or JavaScript, or what do you recommend?
so what I know is like in 11th and 12th grades in schools, they usually teach either C or C++, and for example, like in some of the engineering disciplines as well, they teach C++ or C. But otherwise, nowadays, most of the universities and even some industries, they are going towards MATLAB, because MATLAB is kind of relatively fast, and it's easy to learn. So it's more like a calculator. So it's just you ask 2 plus 3 and it gives you 5. So it's so that's straightforward.
So you're saying it's
So
an easy
MATLAB,
step towards programming. Like,
yeah, definitely.
once you can do MATLAB, you get more familiarized with programming, you can pick up something more complex a little later after that.
Yeah, that would be an approach for sure. But
Mm-hmm.
at the same time, MATLAB is not open source, so not everyone might have access to MATLAB. So in that case, there are a lot of open source which are similar to MATLAB. Say for example, Python. Even Python is very popular. Most of the industries, they use Python because it's open source and it has a lot of capabilities. Some would say it's more capable than MATLAB. So you can always learn Python. It's open source and there is lots and lots of information on Python online, and a huge user data user base as well. But
Okay.
learning C or C++ is will definitely help in learning any of these languages, because these Python and MATLAB are all kind of based on C or C++. So if somebody is like really interested in programming, then learning C or C++ first and then going for Python and MATLAB will be a good approach, I would say. But nowadays Python and MATLAB would be sufficient, because most of the work is done in Python and MATLAB, and always they can improvise on C or C++.
I see. Okay. So one more question that related to programming itself.
Mhm.
So many engineering fields would be probably familiar with some computational methods, but what about biological fields, right? Like if somebody is studying biology as their major, um, are they usually taught computation and stuff like that, or if their college is not teaching them, what are the what's the best way to go about this? What are the
I'm not
tools
sure.
probably used by
Sure.
the biologists, or uh, things like that?
They should have a mathematical model to replicate the cells, or the mathematical model to study how the cells differentiate. And also mathematical models are used to study a population of rabbit or population of humans. So all the mathematical models or statistical models were used to predict how COVID-19 would grow in the world currently. So mathematical models are definitely used in biology as well. As far as I use, so we use so even like a proper like a pure biologist who would be working in lab 24 hours, they would be taking a lot of images of cells or for virus or any of the microorganisms, and they have to study those images. So there are a lot of softwares or commercial programs which does that. So one of the softwares that few of the ones that I used were one is called ImageJ and other was called Cell Profiler. So ImageJ is similar to any image editing software, but it is more dedicated towards biology, because there are a lot of filters that are used in order to study some microorganisms, and to focus on a particular organelle within the cell itself. So that is definitely based on some filters, and by understanding how these filters work, we can uh, separate only those particular organelle. Similarly, there are other softwares called Cell Profiler, which is kind of machine learning based, or they are using some machine learning programs in order to profile the cell. So they will have, as I said, they will be taking a lot of images. Say they take 10,000 images, and then they put all these images in this program, and based on the data set of this 10,000 images, the cell profiler would give us, okay, this is the kind of average behavior of the cells. So that we would understand only by choosing a particular algorithm, and by particular algorithm we need to know what the algorithm is doing. So a little bit background on mathematics is definitely helpful in every field, whether it's biology or physics.
That's very good to know, and this has been very informative that way. It's clarified many questions or many misconceptions I had about either simulations or biology or even a particular branch of engineering and technology that like bio or even a space tech. So yeah, this was a very informative session.
Actually, yeah, I do have a question. So, yeah, I have a couple of questions. Anyway, I'm Shubhojoy, and I do research and teaching in mathematics. So, first of all, thanks for your comments about mathematics being very useful, and yeah, it was a very informative session also. So, thanks a lot. So, I have two kind of related questions. One is, okay, is how much of theoretical mathematics? I mean, do you actually sometimes have to look at actual theoretical mathematics sometimes, like the theory of differential equations or something like that, and or even like theoretical physics, like a general theory of relativity or something? I mean, do you actually have to do that sometimes, or is it sort of inbuilt into the computational tool? So that's one question. And the other one is these about these computational tools. So of course, so these are probably very highly complicated and using of various mathematics and physics and so on. So can you tell a little bit about the history of this? I mean, when did these come about? Because I suppose when NASA first sent people to space and to the moon, these were not around. And so and
Yeah,
are these the software that people they are using, or that you are also using, or what is the history of that? So just these two
sure.
questions. Thanks.
Okay. So to answer your first question, definitely, like when we learn, so at least I can say from my personal experience. So when I started learning this computational methodologies during my undergrad, what I was taught was something called finite element methods. So that's where my love towards this computational methodology started. So the initial course had a bit of theory as to how all this set come together in mathematically it's possible, and then how this can be applied. But that was only a little bit, but more was focused towards solving, say, a particular practical problem in civil engineering. But later when I went to masters, so that was more focused in understanding how this is done, and there I had more mathematics as to what is the space that we solve this problem in, what is the space where we cannot apply this differential equation. So those things were there, and that is necessary, I would say, in order to I mean, even in say civil engineering, we have something called shear force. So the shear force, sometimes the shear force will give, even in commercial packages, the shear force sometimes give absurd values. So we should know why it gives some absurd values, and that comes from how we solve the differential equation. So in order to overcome that, we need to choose some settings in commercial packages. But if we don't know the theory behind it, then definitely we will miss choosing that particular setting. So one of the examples I can give is something called hybrid formulation, where if there's some joint like this where it becomes 90 degree, the volume there becomes zero. Like it's so that kind of points are very difficult to solve, because so in that regard, we need to choose in many commercial packages. There will be an option for hybrid formulation, and if we do that, then it's easy. But if we don't know, then if we just go by tutorials online, then they might have missed certain problem. They would be taking a circular shape. When we go for a square kind of a geometry, then we miss that, and then our solutions are wrong. We'll be wondering why, but we won't understand how to do it. So that's where the theory part of the mathematics would apply. But nowadays, like some like some of the engineers, they'll be trained in the company to solve a particular set of problems, and there would be few guys who are in the top, they will be knowing the theory. So if there is any problem of this sort, then they'll say, okay, just do this, and people do it. So that's how I feel it's happening. But it's always good to know a bit of theory as to how these commercial packages have come in.
Okay,
So
I see. I see. I see.
yeah. And sorry, I forgot your second question.
But with the computational tools that you use, are they the same ones that
Yes,
NASA?
sir. Yeah. The history of the computation tools. As far as I know, the finite element method. So that's one of the very prominent tools used in all the analysis, like structural analysis, and nowadays we do computational fluid dynamics. So all this was generated in 1960s, 1970s, when in Wales, in UK. So there. It was mainly for civil engineering purpose. So if you see any, there are bridges which have like this triangular truss structure. So what they used to do earlier was solve each of these truss structure by hand, and it became tedious when the number of trusses in a structure would be more. So they came up with some writing it in the form of a matrix and then solving this matrix in order to obtain it. So then the computer programs started, and with the improvement of computer hardware and becoming more faster and more feasible, the development of software also took the same pace. So yeah, definitely, like many of this what we do right now can definitely be done by hand, but it won't be as optimized as we do it right now. Like in the programs that NASA or all the olden age space industry did, uh, I would say the ones that we do now is more optimized than what that was done earlier, because definitely it worked. But now it's even more optimized. We can optimize further using these computational tools. So there are like the tools that we use might, like the commercial package that we use might differ from one company to another, but the basic would still be the same. Like how we interpret a result, like, or how the result output file is written by one package will be different from the other package, but at the end, if the vehicle has to, it has to all follow the same physics, and the result will be almost same.
Okay. Okay. Thanks. Yeah, it's about this physics, the the like theoretical, like the theory of gravity that Einstein proposed. Because you're talking about
Mhm.
all these spacecrafts going around in space, etc. So I guess part of your the work is this finite element method, which has to do with stress and strain and all that. So the structural integrity. But what about the trajectories and all? That would probably also involve a lot of this physics and mathematics. So are they all inbuilt into the software and the computational tools you use? Or what is the?
Not uh, I mean, there are a few softwares which does this trajectory tool simulation, so as to decide what path should the vehicle take in order to reach a particular orbit in a most optimized way. But what we are doing is, usually many companies will write their own piece of code in order to optimize it, because it's kind of more suitable to understand what is happening in each and every line of the code. If we know that, then we can optimize it better. So that's the part taken by many companies. So most of the companies will have their own, or they'll have like a commercial company to develop a piece of code for their own, for their particular problem. So when we are writing that piece of code, definitely the physics that is involved in trajectory designing, Newton's laws, like Kepler's motion and all those, will come into picture. But in the stress analysis that we do is, we assume most of the things are static, then we do dynamic analysis for understanding how the vehicle vibrates when it goes through atmosphere, or when we do some experiment on vibration itself. So that's the kind of work that I do personally.
I see. I see. Very interesting. Very interesting. Thanks.
Thanks.
Okay, great. I think there we've had our last question. And, with our discussion initially itself, I think we covered a wide breadth of, various aspects of the fields that you've worked in. So this has been very enlightening and very informative. And thank you so much for sharing it with us and with people who want to learn more about your field and who want to probably enter your field sometime in the future. So thanks again for
Very
that.
welcome, and thank you, Pratiksha, for this opportunity. I hope it has been useful to someone. Maybe it's I'm always open
It's
to
absolutely useful, trust me, because
anyone.
yeah, as a student, I can imagine that, many times you don't get to interact with people like you, and having that interaction is something that will bring a lot of benefits. Yeah. Thank you.
My
Thank you.
pleasure.
Thank you, Pradeep.